Welcome back to Sheldon Exler's Linear Algebra Done Right, and we'll continue to 3D 12. Long story short, I had a fever and I smashed my laptop on my toes, so using a mechanical keyboard and an external mouse, and otherwise the device doesn't typically work, so it's not great. I think last we left off at 3D question 12, I believe. That's where we left last time. So let's continue with that. So it's trying to show that t is invertible and that t1, t minus 1 is equal to us. So this is not necessarily true if stu is equal to I and v is infinite dimensional. I think that's what they're trying to say. So given stu is I and stu are operators over the infinite, let's say v is infinite dimensional now. It's infinite dimensional. And then there exists a scenario where t inverse is not equal to u, composed with s, and there I might say t might not have an inverse. So there's a question to be contemplated. Right. So usually when thinking about infinite dimensional vector spaces, what you sort of want to talk about is the shifting of sequences. Once you manage to shift a sequence, one of the first element of the sequence could disappear, and that can get rid of your invertibility. So I'm thinking along the lines of maybe I want to say t of x1 through x1, x and keeps going. This is equal to x2, x3, etc. Maybe it's like a shift where the first element gets erased and everything gets shifted to the left. And then I gotta compose something with it. So that's gonna be weird. Well, first, maybe that's a bad way to motivate this question, but I'll leave this linear transformation here, and I'll talk about whether us composes t and t composes us is the identity. And maybe find some problems here that can occur given this situation. I'll try to find some gaps here. Because I think what happened here is that if you think about it, then with finite dimensional vector spaces, you know that the kernel of S is equal to kernel of T is equal to kernel of U is equal to just 0. And the reason is because the kernel of I is equal to the kernel of STU. But then the dimension of this kernel of S composes T composes U is actually should be the minimum of actually should it be the minimum? Yeah, I think so, because no, actually they should be added. Okay, yeah, some sort of addition actually, or less than, let's say. I think we talked about this already at some point with two linear transformations, not necessarily 3. But I think that since this holds true, all 3 of these have to be 0. because the kernel of the identity is 0, right? So what that really means is that STU are invertible. Because first of all, they are in the space of linear operators. Second of all, they have kernel is 0. So we know that the dimension of their kernel is in fact 0, which means they are injective, which means they're surjective and invertible. Because surjective and invertible is equivalent to injective when talking about operators. So in this way, we pretty much immediately know that these three guys are all invertible, and we can like perform operations where you sort of just like multiply both sides by something and compose both sides by something like this. And then this is, I think, what allowed you to say that perhaps that t is equal to s inverse u inverse, so t inverse is equal to u s. This is what allows you to, and composition of inverses, these two are equal, so we're good. So I think this is what allows you to say something like that. Actually, I've been trying to project on a big monitor. Perhaps I will go back to using a small monitor because it looks like the font is getting sort of, the writing is getting kind of squished horizontally. So you see that from this we know that t is equal to us. T inverse is equal to us. This is fine. But which part of that proof falls apart when you're talking about infinite dimensional vector spaces? And that's the problem we want to hunt down, right? I think immediately we maybe can tell that it might be the injective implies surjective and what's it called? Surjective and invertible part. That might have been it. Or it could have been this kernel part, right? I think that could also be possible. Why would I say something like this? Well, if you have an infinite dimensional vector space, then the kernel of this is 0. Sorry, the kernel of t is x1. But I think like this is still surjective, right? So surjective is no longer equivalent to injective when talking about infinite dimensional vector spaces. So I already can suspect that sort of infinite dimensional vector spaces breaks down linear operators are it breaks down when talking about linear operators being injective is the same as surjective and also invertible and such. So you can no longer perform such an operation like this because it's not guaranteed that S is invertible anymore, right? This is not guaranteed. And so what you sort of maybe want to say is you want to note that STU is equal to I, but maybe S, for example, does not have kernel equal to 0 in infinite dimensional vector space V. Perhaps that's what you would like to say somehow. I'm trying to think if this is possible. Or maybe what could happen is like U is forward shift by 1, T is backwards shift by 2, and S is forward shift by 1. No, but then you lose the information in T. Yeah, you cannot recover that. Oh, okay. No. So maybe U is a forward shift by 2, and T is a backward shift by 1, and S is another backward shift by 1. U of x1, x2, etc. It's a forward shift by 2. And then T is a backwards shift by 1. And then S is also another backwards shift by 1. So I think that this doesn't indeed compose the identity on this side. But then to check if T inverse is equal to U composed with S, I think it should not, because you already lose information going this way. This is lost, right? Lost. T has no left inverse. So there does not exist a function which you can compose with T such that when T maps this x1 into like a black hole, let's say, where that function can retrieve such an x1. So indeed it has no left inverse, and by the definition of the textbook, it has no inverse, because the textbook only talks about double-sided inverses as actual inverse. So I think that's the problem. Let me actually try to see if I can set up my writing tablet in a better way, because I think that this is not a good way to set up such a writing tablet. First connect the device. Oh wait, this is not the, okay. This is actually a different writing tablet. Okay. The other one wasn't so good. Okay. Suppose B is a finite dimensional vector space and RST are members of operators such that RST is surjective. Show S is injective. Okay, well, first things first, we know that this RST being surjective forces R to be surjective, right? Because if R is surjective, there's something R can reach, then no matter what S and T feeds R, then R won't be able to reach that. So R must be surjective. And if R is surjective, then I think since it's an operator, R is injective as well. And also R is invertible. This is all fine. But now to consider this, right? Now I want to say that for every V in V, there exists V1 and V such that RV1 equals to V, right? Then there also must exist V2 such that S composed of T, V2 is equal to V1, right? Or maybe I don't want to go this way, maybe I want to go the other way around, perhaps. I don't want to say that. Well, Now RST is surjective, and since RST is also really a linear operator, because it's a composition of operators, so it still maps from this vector space to itself, and it's still a linear map. This is a composition of linear maps. What that means is that RST is also injective and also has kernel 0. What that means is that, let me think. I think R and S and T individually all have to have kernel 0 then, right? Because if any one of them, if like say S, if kernel of S is not equal to 0, so let there be V in kernel of S. Sorry, I shouldn't have gone so far. Perhaps I don't want to go that far. Probably I just want to say first that ST is injective. Because if not, ST is greater than. If not, exists V in kernel ST. But V is not in 0. So then ST of V is equal to some W, and R of W is equal to not 0, right? So it's got to be, oh sorry. So this means R composes ST on V is also equal to 0, but V is not equal to 0, so ST is not injective, which means RST not surjective, which is a contradiction. So we have arrived by contradiction that indeed RST must be ST must be injective. Now, if S composed with T is injective, so must T, so must S be injective. That's a question mark. I don't know if it's true. I don't think. Maybe it's not. Okay, no, but if S composed with T is injective, that means T is, okay, so that also means S composed with T is surjective, because S composed with T is a linear operator. And then, since S composed with T is surjective, S is surjective. And since S is surjective, that means S is injective. So we're just using properties of operators, and the injectivity and surjectivity being equivalent when talking about operators. And that's the only way to get around this, I think, because it's kind of screwed up the way this is proceeding in this way. So let's assume that this forms a basis, then prove the map. Isomorphism. It's an isomorphism of V. Okay, no, my computer's lagging. I don't think it can handle the monitor being displayed as the same time as this video. So I think I'll stop this video and cut to just using my laptop.